Lab 2 of motion of a falling object. The purpose of this lab is to analyze the motion of a falling object with and without the drag force. The force of gravity causes objects to fall towards the center of the Earth. The acceleration of free-falling objects is therefore called the acceleration due to gravity, as the force of gravity causes the object to accelerate. But as the object velocity increases, it encounters air resistance or drag, which opposes the motion. The magnitude of the drag depends on the square of the velocity, and the drag increases until it is the equal to the weight. We are interested in this lab because it shows the impact that drag has on objects in motion. This information is important to understand for large-scale aerodynamics on objects like aircrafts. In this lab, Newton's second law of motion, F net equals mass times acceleration, will be applied to analyze the motion of objects that are falling under the sole influence of gravity and under the dual influence of gravity and air resistance. Here are the following equations we will be using. We will be using Newton's second law, which is also written as V final equals V initial plus F net over m times delta t. This determines the final velocity, and this final velocity is used in the computational models and further inputted into the position update formula under a while loop. The F net is not constant in this case and includes both drag and gravity, which is shown in the free body diagram to the right. The gravity and drag force is the opposite. The drag force formula is the following, where B is a constant, and it is b times velocity squared. The gravitational vector force formula is the following, where it's negative m times g, and g is also a constant, which is 9.8 meters per second squared on Earth. Now, in order to conduct this experiment, you need the following materials: a weighboat and a recording device. So you're supposed to drop a weighboat or any object from a height and record the motion, import the video into Tracker, adjust the start of the video to begin with the motion, and track the center of the weighboat at every time step. You're supposed to construct two computational models, one with gravity and one with gravity and drag. Transfer this data to an Excel sheet and analyze it. Now here's the initial data. The video that is analyzed is 0.833 seconds, and the initial Y position, which is what we were focusing on, is negative 0.0019 meters, and the final position is negative 0.6353 meters. The axis is oriented to include the object in its first frame as close to the origin as possible. The initial velocity is 0 meters per second, and the initial mass in SI units of the weighboat is 0.00022 kilograms. Now here's the video that was inputted into Tracker. And I basically tracked the center of mass as it fell down. Now, as you can see, this creates an exponential decline because the velocity is constantly changing. Now, there were two computational models created, one with just including gravity and one including gravity plus drag. Now, this is the gravity computational model. The initial conditions are the same, where the delta t is 0.033 seconds and g is the acceleration constant on Earth. Our j hat vector, which is the unit vector for the positive y-axis, is 0, 1, and 0, and b is 0 since drag is not included in this computational model. In this computational model, the only force is gravitational force, so F net equals gravitational force, which is W. This computational model continues to output positions under a while loop at every delta t time interval. Now, if you actually compare this model to the experimental model, you can see that according to the model, it overpredicts the falling distance. This means that air could exert a force which is known as a drag force, and as a result, we create another computational model. Now, before we move on, this is the data that was outputted from the gravity model, and as you can see, this is the graph and of position versus time. Now, the initial conditions of the gravity and drag computational model remains the same, with B changing to 0.0036. This will ultimately improve our model to match the experimental model. Now, FNet will actually will include gravitational force plus drag force. The drag force formula is the following, and FNet has changed. Now, under the while loop, Newton's second law will occur and update the position at every time interval. Now, here's the position versus time graph that occurs from the second computational model. Now, if you take a look at the final results, you can see that gravity plus drag force is more similar to the experimental data. However, there are still some deviations which can result from error while documenting the center of mass. Also, air resistance is probably not affecting the objects equally across the entire surface area. Now, what does this all mean? So which model predicts the terminal velocity? None of the models run long enough to predict terminal velocity. In the case that the velocity is high enough in the drag model, the slope would eventually hit a point in which the slope is truly constant, which would indicate a terminal velocity. The velocity is the derivative of position, and because of this, there would not be acceleration, as it is the derivative of velocity. If an object is thrown downward, will the terminal velocity be the same or different than if it was initially at rest? The terminal velocity will be the same in both scenarios because terminal velocity is not impacted by initial velocity. When the object is thrown with an initial higher than the terminal, it would slow down until it reaches the original terminal velocity. Now, some future improvements we can do with this lab, again, is use a different object and seeing how gravity and drag affect that object. And we can also use a more specific proportionality constant, since ours was kind of derived from plugging in various numbers to see which one match the experimental position the best. Thank you for listening. Have a good day.